Okay, so welcome everyone. So our next speaker for the day is Dhairya Gandhi. So Dhairya is currently a data scientist at Julia Computing Incorporation. He's responsible for maintaining and developing the FluxML stack at Julia. So over to you, Dhairya, for the presentation, and welcome to the Software Freedom Day.
Hey guys, I hope all of you can hear me. Thanks for the invite. I'm really happy to be here. And thanks for the introduction. My name is Dhairya Gandhi. I'm a data scientist at Julia Computing, as well as the maintainer and developer of the Flux ecosystem, essentially. And we'll speak about that as we go forward. Um, so I just wanted to basically structure this talk along the lines of, how programming and how, actually production systems have been built over the, past decades and how they're changing, and specifically how, the things like machine learning have, evolved so far. And so how all of this fits in is basically part of the talk. So part of it is going to be what Julia is all about, like as a language, why it's necessary, and after that, how it impacts things like machine learning, things like these new algorithms that people want to develop, and how the whole concept of differentiable programming comes and is being utilized in the larger context of things. Hopefully, this wouldn't be too daunting as a as an introduction, but please feel free to shout your questions at me. I'm happy to take questions and comments throughout the talk, and hope that everyone gets to learn something and it's fun. Okay, let's get started. So, why was Julia created in the first place, right? So, how software has been developed over the past decades has been that you have these specialists with a lot of domain knowledge who encode a lot of information into these algorithms that they build. Now, these algorithms could be about performance, they could be about solving a particular problem, but one common thread that they all have is that they're developed in a high level dynamic language, and the reason for that is that because those languages are high level and dynamic, they allow for a lot of flexibility across algorithm development. But typically what happens is that these languages lack a lot of the feature sets that are required to actually make them performant, and which means that once these algorithms have been developed, you're shipped off to an engineering team who will rewrite the whole system in something like a low level language or something that is actually performant like a C or a C++, and then it's deployed. Whereas in the Julia world, it's often called that Julia is a very, very greedy language, right? Because what it tries to do is it wants to have the ergonomic high level syntax, the dynamic nature, but at the same time keep the performance of a very, very tight C code base, right? And not only that, it means that all the algorithms developed by these domain experts can now directly be shipped off to production systems, which cuts down on the time to actually bring something real out into the market. And that's a real large achievement, especially for something which is very, very time sensitive. And also it means that we'll see how specific features of the language make it so that we can express concepts which are either very difficult to express in existing languages, or they require multiple languages to be brought in. So this is known as the two language problem, right? So like anytime you want to bring something real into the world, not only do you have to have the expertise to now develop these algorithms, but also have the expertise to make production systems out of them. And deploying them is an entirely different story altogether, right? So this is a very simplified chart essentially, but the crux of the matter is that we want to streamline this whole process to have just one language be used across all of them in a manner that it makes sense and can be we don't lose out any performance. At the same time, we gain back a lot of productivity and accessibility. So talking about some of the journey. So essentially, these four folks here that you see here, Viral, Allen, Jeff, and Stefan, were the creators of the language. This was back in 2009. Um, for folks who are used to using Jupyter notebooks, the Ju in Jupyter actually does stand for Julia. And as you can see, in 2018, the language reached the 1.0, which essentially basically means that there is a guaranteed stability in the APIs of the language. Um, what it really tries to show is that there is enough maturity, not just in the language but also in the ecosystem, to actually support large scale problems. And having said that, those kinds of things have always been part of the language design in terms of maturity and scalability. But it brings a whole next level of confidence in saying that we now believe that we have something which is worth sharing with the world at a very, very large scale, right? Um, in 2020, Julia 1.5 was released that had a bunch of really cool functionality. We'll probably speak about that later. And as you can see, this slide is just to show like some of the companies that have ongoing and existing projects with Julia. And as you can see, there's a lot of well-known names in there, shall we say. Not just companies, there's a bunch of universities that employ Julia, either in a pedagogical sense and in an academic sense, but also for research, also for different projects that they are very much engaged in. And as you can see, it's some of the who's who of the world. Not just that, it's spread out globally. Uh, it's basically to give you an idea of the spread of the language thus far. Not just that, Julia is a very young language, like we discussed, right? Like it's been less than a decade essentially when it achieved what we would understand as something of a good scale. And even in that point, it's ranked really, really highly with some of the best known languages out there. So you have Kotlin, Rust, Julia right there. And of course, this is something, this is based on the IEEE Spectrum language rankings, by the way. Uh, Also, as it goes, Julia received 10 million downloads, 3,000 packages used by 10,000 companies. So this is to show that the scale of this growing language ecosystem is actually not just vast but also very rapid. As I alluded to before, the Julian syntax looks very much like a high-level programming language would. And I mentioned earlier that Julia is a completely dynamic language, but that does not mean that it does not have a very, very rich type hierarchy and a type system. What that basically means is that people who are used to writing, say, a Python, Python style of coding, will find the Julian syntax very approachable. But at the same time, you have the kind of control over your types and making sure that you can exploit them the best with Julia. At the same time, this is not something that the language enforces. It's completely up to the user on how they want to use it, completely generic, as well as providing for cases where you can exploit the exact data structures that you actually require to solve a problem. So as you read here, there was a Nature article that was covered by the Nature Journal, uh, calling it "Come for the syntax, stay for the speed." So as I alluded to before, the syntax is something which is very, very approachable, but the performance is something that you would get out of a much more developed language, so to speak. There's plenty of books on Julia. As I mentioned earlier, Julia is used to teach in many, many different domains, not just for specific cases like numerical compute, which it is highly, highly well suited for, given its speed, given its throughput and performance, but also relevant for many, many different domains. For example, you have works like operations research, or for that matter, computer vision. In fact, Julia has some of the most advanced bioscience libraries out there. It has some of the most advanced quantum circuit designing software out there. It has some of the most advanced differential equation solvers out there. So, what do I mean when I say that we need a language for AI? And it's not just me who says that at this point, right? So here you have some of the who's who of the ML world, so to speak. So people like Jan LeCun uh, have stated multiple times that deep learning, as we know it, has kind of become this buzzword which actually has very limited use. But the real you know, catch here is that differentiable programming is the next wave of software development that is going to see a very, very large impact on how not the software is developed, but how all of these programs are essentially thought from the ground up. Similarly, Andrej Karpathy, the director of AI at Tesla, uh, you know, basically also echoes the fact that we need not just very very high levels of computational resources, but we have to make sure that the software isn't doing unnecessary things, that it actually has the requirements to fulfill a very large search space, but also make sure that we can do it in a feasible manner, so in an ergonomic and simple manner. um, Chris Latner, very famously known for Swift for TensorFlow, also speaks about how Julia is very capable of a language for the future for this domain essentially. Jeff Dean talks about how Julia has been applied to TPUs before, and TPUs are some of Google's tensor processing units built specifically for accelerating machine learning tasks, really. And the idea, Julia was only the second language to ever be run on a TPU, if I recall correctly. But what the idea really is that a language that allows you to be expressible to allows you to have the amount of flexibility in handling the internals, also allows you to target different systems very very efficiently and quickly. So the turnover period there is very small, and because of the way Julia is structured, for example, with the use of multiple dispatch, it means that we allow for the reuse of code very, very aggressively. And generic functions are something that are not just expected, but also encouraged to be used in Julia. So you'll see how what I mean by that. Okay, but it also means that we're not limited to whatever the language, so to say, gives us, right? So we can go out and make it so that the language can actually you know develop code that is written for CPUs, also target GPUs, also target tensor processing units, and so on. So that's a very exciting area of ongoing development as well. So this was in 2018, and yeah, so as I mentioned before, you have some of the who's who of the computational sciences world all talking about Julia. As a matter of fact, some of you might have heard of Jeremy Howard, the guy behind Fast.ai. He has recently been speaking about how Python is not going to be the same kind of ecosystem that it needs to develop code for the future of ML. And Julia is one of the languages that he sees as very, very likely to take part in this process. In fact, recently he has also expressed that interest on Twitter very publicly. So, as I mentioned before, Julia is designed for speed. Julians are very greedy programmers, as we say, and what that means that we have some of the most state of the art performance out there for many different tasks, not just in numerical compute, but and as we know that performance for a large system does not come from one fast core algorithm. It comes from the entire pipeline to have that kind of polish, right? So you have some of the fastest CSV loading out there. You have some of the fastest graph processing out there. You have some of the fastest clustering out there. So these are just examples, right? These are just supposed to be very, very fundamental things that a large scale numerical system will end up doing. And as you can see, the benchmarks game also shows that Julia is much faster than the competitors that it is actually being compared to for the most part. And all of this is, my long way of telling you that not only is it a language mature to do a lot of different tasks, but also do them well, also beat the state of the art at the same time, have the kind of expressibility to, it, to move into the future rather than and act as a toolbox in your toolkit rather than something that limits you. So Julia 1.5 was released, and the authors of Julia, the language, won the Wilkinson Prize and the Sidney Fernebach Prize, all very, very major props in the scientific community. And as you can see, when I say that a language that is approachable enough for folks to actually take up, and we use the same generic constructs across the ecosystem, not just the language but across the ecosystem, it means that any kinds of improvements in the language also permeate through its packages very, very rapidly. So as you can see, just between 1.4 and 1.5, we see major performance improvements right out of the gate. So here's a bunch of, like a little release summary, but again, all of this is to say that it's in very, very active development. Um, People who are interested might also have heard of, the computational thinking class, which also has Grant Sanderson from the Three Blue One Brown fame, who is teaching a course using Julia. And all this, again, basically tries to show how far apart it's spread, really. It has its own system of notebooks, of reactive notebooks. Jupyter, obviously, is one such system, but it's not limited to just that. So, excuse me, Pluto is another ecosystem which allows for reactive programming so that whenever I make changes in one cell, that change is reflected throughout my notebook development process. The idea again for that to show off that we can have these very generic constructs in a language that allows people to do all of these things fairly simply. So as mentioned here, it is written completely in Julia and is, you know, it's it also has this very friendly UI. So it's been used in a very, very different number of problem sets really. Julia can, need also target GPUs. Specifically, I think the Julia GPU organization is one that, works very closely on making sure that we have some of the state-of-the-art performance rivaling that directly of CUDA C. Not just that, we can write kernels in pure Julia, which will be targeted to the GPUs directly. So it does not only, depend on the CUDA driver, so to speak. We can generate code directly to target the GPUs as well. And again, some of the recent updates. So CUDA 11 was introduced as uh, you know, supported version for CUDA. Also, along with all the backwards compatibility that comes with it, you can target multiple GPUs at any time. You can target a GPU per task, and it has been used in a multiple of different areas, specifically in pharmaceutical research, and in cases where you need a very, very large number of resources, right? So where you can presumably target hundreds or even thousands of GPUs at any given point in time. And again, the idea of that is to show how the language constructs are able to handle all of these things very easily. So now coming closer to the question at hand, data science. And again, as you can see, dataframes.jl along with csv.jl outperforms, things like pandas completely. It basically overruns it completely by up to 30 times actually. And this is just again a way of showing how across the stack, you need to have this kind of polish and this kind of finesse to make sure that not only are specific for loops fast. That's not all that we're looking for, right? We're looking for performance across the spectrum, and that's what makes the actual output and the actual applications fast, not just one kernel. Right. So back at AI 2.0 and differentiable programming, so one reason for that was that current approaches so far have relied on brute forcing a bunch of specific constructs to be used only in the context of machine learning, in the context of a learning algorithm, whereas in the past multiple decades and where optimization has been the bread and butter of the scientific community for a very long time, you have these fast but very limited methods. And recently, there was a need to actually target both of them at the same time. Reason being that as research goes on, we realize that there is so much more that we can do with the existing machine learning that knowledge that we have, but we can also integrate a lot of these scientific softwares to make use of them to apply machine learning in many different domains. And why Julia comes out ahead is that not only is it great for numerical computation, which is what both of these universes are are going to use a lot of, but it also means that because it has those generic constructs behind it, we can actually merge them very easily in a manner that you can extend very reliably as well. So as you can see, why Julia? It's because it's fast. That's one of the biggest reasons, of course. It's easy to use. Productivity is off the charts, scalable, and it supports the different kinds of hardware that are coming out. So be that different kinds of CPU architectures, GPUs, even the latest iterations of them, as well as things like FPGAs, as well as things like you know all the TPUs that are out there, which are designed for very specific workloads. So what is next in AI really is? And the answer to what is next in AI can basically be found by what AI has been doing so far. And I say AI in very broad terms, but really what I'm talking about are these simple mathematical constructs that have grown in the past decades and how we use them today. So convolutions are a very simple example of them. And the whole idea behind them is that we want to encode some amount of structure, and we want to understand not only how does this structure come up, but how it relates to other local structures across, say, an image. Now, this is one very simple example where a convolution would try to run things like abstraction, things like higher order features, to find these higher order features, to separate these spatial features. But the whole idea behind this is that we want to encode the structure. Uh, Now, to encode structure, the way we want to do it in Julia is via the stack of Flux and Zygote and all the other packages that we have developed so far for this exact purpose. And we want to talk a little bit about how differentiable programming is basically a generalization of what machine learning has evolved to become what it is today. So we spoke about how structure is important, right? And structure doesn't just come from having these very well-defined images as our problem set. Structure comes from understanding what the problem is that we're trying to solve, right? And as you can see here, this is a GIF of a trebuchet. So basically, the idea is that we have some weight and some force that we're going to put on this little rock here. We have a target, and the idea is that we want to throw this rock and hit the target. As you can see right now, there's nothing much happening, right? There's little to no knowledge that is that's being used to actually inform what kind of forces that we're supposed to apply to this rock to actually get it to hit the target. Now, the interesting thing here is to note that we are, if you look at the code snippets on the right, in the aim function, we have this we have this argument called wind. So it means that not only are we going to model what the trebuchet is doing, but we're also going to be counting in external factors such as wind, the direction of wind, how fast it's blowing, things like that. And one thing that I want to point out very specifically is that the way the equations of motion that we've learned uh, across school basically govern the same this entire simulation really. So how we model it is with the help of ordinary differential equations, so ODEs. And the idea is that we have these ODEs that we try to solve, and if we solve them just right, we're going to be able to, know, given the wind, given how far away the target is, how much force to put on this thing, at what angle we're supposed to aim at to actually hit this target, right? Now, in order to do that, we have to train this ODE to get the parameters just right. And what we're going to do is we're going to replace part of the system with a neural network. And why we do that is because, earlier on, if we had to do something like that, it meant that it used a large amount of compute and resources to train a very simple problem like this. But because we're going to be only encoding very limited amounts of information here, specifically the angle and the weight, we also have a lot more explainability around our model, so to speak. So we have a neural network which will, which will train essentially, which will also account for, concepts like wind. As you can note, not only as I mentioned before, this is just an ODE. This software was never written with the thought of having anything close to doing machine learning close to it, right? The idea was that you have an ODE solver and you solve that ODE to hit this target. That's all. But what we've done uh, by extension is we've added a little bit more complexity, right, by the ways of neural network, to find a loss function, which folks who have noted before. So basically, looking at how, given certain parameters to the model, namely the angle, the weight, the distance, the wind, how far away did we end up landing? So like, what was our error in um, compared to where we wanted to be, right? So yeah, so we've added all of these things, and as you can note, this was done completely without the knowledge of having any machine learning in, involved. But once you train the system within the Flux and Zygote ecosystem, what you realize is that not only can you do it, but you can do it very efficiently, because now not only are you not expected to solve a very resource hungry ODE, you can do the whole amount of training by just simulating the system and getting the the model parameters back into the model, and that way we have a lot more control and a lot more explainability about what it is that we're trying to learn. So this is a simple example of the same kind of idea being applied to the cartpole. So the cartpool is a very simple game. You have a base and you have a stick, and basically the idea is that you can either move the base left or right, and you want to do it such that you keep the stick straight up. And by simply again encoding the physics of the simulation essentially, right? So as you can see here, again what we're trying to do is we're going to understand the physics and we're going to simulate the physics really well. And the same thing applies here. We want to simulate the physics properly, right? And this is typically, not done this way in the sense that we have our environments already specified, and then we have a model which typically has to, use something like a reinforcement learning, which would require a lot of non-trivial, code to be written to handle this one particular environment. But it means that it can't be extended to anything arbitrary in the sense that, this is very limited semantics that we're dealing with. However, in the case of differentiable programming, what we're doing is we're going to tell the model everything there is to do about this environment. So like, given every time I move the stick left or right, how, what forces actually, are applied on the stick at that point and how it reacts. And what we've learned in our research so far is that where reinforcement learning, a typical model would take something like 400 episodes for it to solve it, differentiable programming can do it in 6. Oh, we have some questions along here. I'll probably, answer them at the end, basically because, I would really like to speak a little bit more about Zax as well as we go forward. Um, is it really time to switch to it from these frameworks? Actually, there is a lot of reason why you would want to do it at this point, actually. So yeah, let me address these questions in a little while. But good questions. I really do want to take these up. So I spoke about how differential programming can be used in a larger, more structured context. But let's start with something more reasonable, right? So like writing a custom loss function. So typically, folks who have used TensorFlow and PyTorch extensively would be familiar with a lot of these loss functions that are predefined for you. So, we want to, and one of the typical things that happens inevitably in a program, in a real world application really is where you want to, understand the metrics that you're dealing with on a much more, granular basis. What that means is that you typically have to write a custom loss function. So we're going to be starting with that. Actually, you know what? No, let's not. Let's do custom everything. And the reason I say that is because not only is it just that the loss function is a very, very fundamental part to the learning process, it's limiting in the sense that we also at some point in time would want a layer which does something very specific to our problem case, right? And not only that, what I'm trying to say here is that models as we know them currently are, that thinking is kind of flawed when we say that we have a model which is very deep, it has layers upon layers upon layers. um, that's that's okay, but what it means is that we're going to be limiting our understanding of the model to this particular little area where all the machine learning is happening, so to speak. But that is simply not the case because we have all of this domain knowledge strewn across the board in software developed uh, for decades upon decades upon decades, with a lot of research gone into it and a lot of optimization. Why should we not be able to use all of it? So the idea is that we want to think of any model as basically uh, a system of transforms. So I have some input X, I want to do F, G, and H to it. It doesn't really matter what it is. Is it a linear layer? Is it a convolution? Is it an ODE solve? I just don't care. To me, everything is custom, right? And a very simple example of this can be, as a demonstration. So someone mentioned about, where, if you want a custom loss function, this is just as simple as writing this, right? How hard can that be? And if you notice here, this is the Julia version at the bottom. They're not too different, are they? You have a torch.mean and the same kind of semantics, only you convert them to Julia, and you have a working loss function. Everything works. What's the problem? And the problem that I want to talk about here is calling this little bit here, the torch.mean, and the consequences that that has really. Excuse me. What it means is now output and target are not just normal things that I'm used to seeing that the language provides for me. These are tensors typically, and not only are they tensors, there's specific tensors provided by the library itself. And further, torch.mean works, but if I had a mean from a completely different package, which which I might as well want for maybe they've figured out how to make mean the fastest mean that they can be. Why should I not be able to use that, right? But the thing is, now I'm limited to using the operations provided to me by this framework, and that's very limiting in terms of doing anything new. And here, when you compare that to Julia, you see that that is not the case at all. You have X and Y, and I know you don't have types annotated everywhere, but take my word for it, and please don't take my word for it, do it for yourself and find out that X and Y are just normal arrays that Julia would already have. And the mean is just the main function that, again, Julia already has in its 100 libraries. There is nothing special about these functions, so to speak. And not only is there nothing special in terms of, what the types of these things are, we can also support types which we've never seen before, as long as the computation works, right? So as long as you can tell me how to subtract element-wise two things of completely different types, as long as I know how to calculate the gradients for them, I will not worry about uh, what those types are. And I do know how to construct the gradients for them because I will have the information via method overloading essentially. So any function here, and Julia has this concept of generic functions, and every generic function can have an indefinite amount of methods associated with it. What those methods do specifically is related to the kinds of types that that are input to it. What that means is that as long as I see a method that takes these types, I can recurse into it and find out how to convert that into basically something that can provide the gradients back for me, and that's all I really need. And this is done via adjoints in Zygote. So another practical limitation of the way we do things right now is that we need to write a lot of custom code essentially to do things which are very simple. So linear layer, as you would be familiar with, is this whole thing that MLPs and things like that were based off of. So WX plus B is the one equation that changed things for the better, I suppose. And to do that, this is straight out of the PyTorch docs. Basically out of their GitHub. Essentially, if you go there right now, this is what you'll find in terms of how linear layer is defined. And you would find that not only are you expected to write all of this stuff here, it also goes back to a forward function. Why is that? Nobody knows. That's just how they've done it. It means that this is the forward pass that will be run, but essentially it also means that we have to now write all of this boilerplate code rather than doing what I want to do, which is train my model, right? So this is just for developing custom code, for example. And as you can see, the linear operation itself has a lot of things specific to Torch again. Um, why this is necessary again to handle different types to make sure that we are going to dispatch to the right methods, make sure that those methods are written in C because it's going to want to be fast, have different cases for different types. So the rank of the matrix is important. How do you handle biases? All of that stuff needs to be taken care of explicitly in one place. Okay, so this is how we do it in a traditional framework, right? And this is what the layer looks like in Julia, essentially. And actually, this is not even how the layer looks like. This is just what I wrote. And for better or for worse, this is exactly how it works even in Flux right now, and getting you the same performance as anything else out there. So you have the activation function, which is applied element-wise to WX plus B. And that's about it. And that's the maths that we want to deal with. So another thing that it shows you is that Julia, while being fast and while being expressible, it is also very similar to the maths that we're trying to do. And typically that will be the case, right? So not only with the maths, but like many times you have people who want to apply language constructs like parallelism, like threading, like having a million workers across a million cores. That's something that we have seen in many cases. I would actually point you to the Celeste project, which showed that Julia had joined the petaflop flop, as it's called, basically doing the petaflop worth of compute. Um, and again, all of these things are based off generic functions, which mimic not only the maths that we're trying to do, but also show off how all of these things are built. And the reason all of this works so well is because of how we calculate our gradients is one of the cases, and it's one of the most interesting cases. It's done via this whole system called automatic differentiation, and it's nothing new. Even things like Torch runs on AD, so does TensorFlow, and so does Flux. Why is Zygote, which is our AD framework, why is that any special from the Torch AutoGrad? You would ask me. It's because of our host language, we're able to leverage a lot of the language constructs directly, not have to worry about what kinds of things we're going to be input. The fact that we can look into the intermediate representation that the code generates at very, very fine grained scale, we're able to generate very efficient code. And that means that we just don't have to worry about uh, half the things that a language like Python might restrict you to. At the same time, because of Julia's compiler, we also make sure that we get the optimizations in that actually make it really fast. So a function like this, which has no type annotations, which has no special tensor types, which have no special parameter types, although we have helpful helpful functions available to capture all of this information, because it is relevant to the study at hand, it doesn't mean that we're going to be limited by it, right? Like, so right now, even though I have a function that assumes nothing about machine learning specifically, I'm still able to differentiate through it, and that's a big deal. What that enables us, you would ask me? So one thing is that we have worked very hard to make sure that all of the different functions provided by base language are covered, right? So all we really have to worry about is constructing the backwards pass for the multiplication, for the addition with this little dot here, the broadcasting, as well as the broadcasting for whatever this activation function happens to be. So that could be a real user node, whatever, right? All that means is that as long as we know how to capture the language properly, and when if I have a special kind of w and x for performance reasons, for for my problem reasons, any reasons, as long as I have a multiplication operation defined, I can also generate backwards passes for it efficiently. So this is all to say that because we're not going to be treating only just the base language, but also the larger ecosystem the language has fostered over the years, we get for we get to apply the same concepts to many different domains. So this is what brought on the revolution of scientific machine learning. So scientific machine learning is a fairly new concept where you have a lot of these very complicated differential equations solving for different domain problems. So be they battery modeling, for avionics, for pharmaceutical research, for drug discovery, for COVID research, whatever basically fancies your fancies your liking. And what we're able to do because of our generic AD struct is that we're able to take all of those parameters in and chuck it right into the language itself. And because we're again encoding the structure of the problem much more faithfully than a simple MLP would have, we're able to train uh, these complicated models. So for example, this is an example of a predator and prey system. We're able to model it efficiently with a very significant speed up to boot, not just because of the language, but because now we're fundamentally solving the problem in a very different manner, which is vastly more uh, granular in terms of the knowledge that the model essentially has. We're basically treating every little line of code that you write as part of the model itself. As a matter of fact, the whole concept of a neural ODE won the 2018 NeurIPS Best Student paper as well. So some of the folks, working on that were also, very, interested in how all of these things were working. So that's one of the reasons why we aim to support it that well. And because of its generic nature, not only are we able to support ODEs being generic, we're able to make it universal across the entire differential equations ecosystem essentially, which again exploits things like parallelism. Excuse me, which again exploits things like parallelism, things like recursion, control flow, custom types, whatever. And all of that is things that we aim to make sure that we have a very firm grip on. We are able to train our models and get the speed ups as well as get better results out of it. So that's a little bit about scientific machine learning. And but that is not to say that we don't do traditional deep learning with Flux anyway. So as I alluded to before, we don't see differentiable programming as a specifically different thing, so to speak. We see it as a generalization of the concepts developed so far for deep learning, and those are very, very essential for progressing as we do in the future. So things like training large scale ResNets, things like training large scale transformers, GPT, whatever, are things that we are definitely interested in as well, and we want to do them in a very, very performant manner to boot. As you would note in this little blurb that I've written here, my predict function looks awfully similar to what I had for my linear layer, right? WX plus B. My loss function is, again, I've written hand coded. You'll notice that there is no uh, thing, so to speak, that I've picked out from Flux specifically. So there is no torch.mean involved, for example. And we're able to take the gradients of it without too much hassle. Again, this parameters object is just to make sure that we're able to capture all of these things in one place. But again, you don't have to use it if you don't want to. It's completely and 100% supported to completely forego that. And this API call changes slightly, but again, that's just the API. Flux comes with a bunch of these layers that you would expect from a modern machine learning platform. It has a bunch of these optimizers, some of the latest ones, some of the different SKUs that you would expect. So be they local optimization routines or global optimization routines coming soon. We have all of these things baked right into it, along with specific ways in which can extend it without having any assumptions made by Flux at all. So it also has a very simple Keras like you know uh, basic API, so you can write your models as a sequential. So we call it a chain, but the sequential you would be familiar with is how we would do it. Not to mention, because of the way that our approach has been modified over time, you would notice that it is significantly more simple to write Flux than it is to write PyTorch, for example. So the barrier to entry, not just for development, but also for extension, is very low. And as you can see, Metalhead is one of the projects that provides a lot of these computer vision models. So your ResNets, your Inceptions, uh, your Google Nets, all of that stuff, VGGs, YOLO, specifically for YOLO, Object Detector again does YOLO stuff, .NET for .NET models, Transformers for Transformer models, Symmetric Flux for graph neural networks, so on, so on, and so on. You have UNets, WaveNets, attention networks, Transformers, as I mentioned before. So there's a whole ecosystem of models ready for you to use. Um, I would recommend that you check out the Model Zoo for more examples. The website has a lot of documentation, and yeah. So this is just like a little, you know, a little. I've just picked up some of the projects that I had tabs open for honestly already. So you have things like Flux 3D here, which is specifically developed for working with 3D data. Um, so point clouds, mesh type data, and also what we found in our systems is that not only did we not have to write anything which is very, very catered towards doing differentiable programming, we were just writing something that was going to work well on 3D data. Not only were we also able to differentiate it, but we were able to do it in a very, very performant manner, targeting GPUs, targeting different hardware out there, while also making sure that we were able to beat some of the state of the art existing implementations of these stacks. For example, in Kotlin, which is developed by NVIDIA, so and uses Torch on the backend. So SciML, I spoke about them before. Turing is for probabilistic programming. Geometric Flux is for graph neural networks. Transformers for transformers. Excuse me. We also have an incoming port of FastAI. As I mentioned, Jeremy Howard is very interested as well. So FastAI for a higher level API for learning a bunch of these things. Object Detector, Metalhead, AlphaZero. AlphaZero, we'll see just in a moment what it's all about. And there's frankly many more. yeah, it, these were not only some of the open ones, but also have nice, pretty logos for me to work on. So not only is Julia great for all of these things, what you will notice is that there's a vast ecosystem of state-of-the-art optimization libraries developed in Julia via this organization called Jump. And if you want to work on different kinds of optimization routines, there they have some of the most comprehensive toolkit available to do that in any ecosystem today. So Jump is specifically for mathematical optimization. It won a bunch of awards. It has a bunch of backends, and as I alluded to before, they can solve many different kinds of optimization routines, and many of them locally even. So SciML, you're able to connect scientific software with new age machine learning while using things like modeling techniques and simulation techniques, while targeting GPUs and using automatic differentiation to boot. So a lot of these applications require work on model battery models, for example, on climate research, on you know on so DSG modeling is basically for financial modeling and trading essentially. Pumas is another one of those packages and ecosystems developed for pharmacometric research and so on and so on and so on. So like even robotics, you have differentiable robotics today. So yeah, that basically goes on to show you that not only can it be performant, but also it has this vast ecosystem available already and is actually performing at state of the art or exceeding it, basically becoming state of the art in itself. So the ecosystem problems that people spoke about, I hope it brings some kind of you know insight into where we are there. So as I mentioned before, AlphaZero. So this was developed by John Laurent, and basically it's a Julia port of the AlphaZero, excuse me, of the AlphaZero algorithm developed by DeepMind, and it is a very simple and extensible and a generic um, package if you actually go and look at it. But the cool thing is because it uses all of these things in the back end, what we're able to do, AlphaZero is a very resource hungry thing to train. Trust me. So the idea is that this is a game playing AI. So you would have heard of, AlphaGo beating the world's best Go players. But AlphaZero is developed as a generalization of that same fact, basically making it so that even if you have zero, you know, knowledge of what the game is really, the the model itself is able to learn a lot of these rules and get better at it. Um, so that's where basically the zero comes from. It has zero experience. It starts from scratch. What it means is that it needs a really ridiculous amount of computational power to train, specifically because you're learning a lot more than just one game at this point. But this way of doing things makes it 10 to 100 times faster than other high level alternatives, straight up. Um, and again, you know, it means that there is not one place where you would run it. There's no one machine in the world that you would specifically use for just this. Mostly because that would be wasteful in terms of how it would be trained. But what you want to do is really you want to pull up some cloud resources essentially from an AWS, from a Google Cloud, and you want to get a bunch of these nodes and you want to chuck your program right there. So that's essentially the idea of it. So as you can see, this is Julia Hub, which is one of the things developed by Julia Computing. But the idea again is that you can request for GPU resources. You can have a large number of nodes that you want to run it on. You can specify the kind of memory layouts that you have for the hardware that you want in there, and you can just start a job with just one click. So actually, let me quickly show you If I have this open, maybe I don't. Right. This is here. I don't know if people can see my screen right now. Okay. So that was the idea of our talk so far. Thank you so much for joining me. These are some of the more enterprise level features and products and services that Julia Computing offers, specifically for working on not only large scale compute but also management and so far. Um, yeah, we can we'll be happy to get in touch with you if you have any questions and yeah, thank you.
Yeah, thank you very much for this wonderful talk, Dhairya. So we can take a few questions from the chat and Q&A.
Yeah.
So,
So,
yeah,
so one of the questions that I see right here, sorry about that, I cut you off, is what are my views on JAX versus Zygote, and what about benchmarks? And how does all of this compare with TensorFlow? Okay. And the simple answer to that is, well, JAX is built upon the whole idea of doing partial evaluation, right? Is that you want to build this computational graph before you execute the programs, and the idea is that you can use a lot of these optimizations that you already know for things that you can do for linear algebra essentially. And the thing is that those things apply to Zygote just as well. And even though there are some cases where you would find that because they're able to optimize for one particular problem you know more than other like a torch might have. Uh, it basically Zygote works as a kind of a generalization on JAX as well, because if, for example, you wanted to do things like control flow, JAX would not be able to handle it properly. It's because of the kind of IR it is generating for the kinds of operations that we're dealing with. Whereas those problems just don't exist with Zygote because it is dealing directly with the Julia IR rather than generating its own. And even in times when we do generate our own for many reasons, we make sure not to change the semantics of what is being done, and that has held true for the vast applications that we've developed with it. Speed wise, actually, let me see if I can bring it up. So Zygote actually has some of the fastest, launch times. So like the AD overhead that people talk about very frequently, that is almost different on the orders of magnitude in this case. So for example, let me show you something. So this is how you would. So this is just for. Excuse me. This is just for Julia, but I do have a slide specifically for. It is not in here. Okay, so suffice it to say that Zygote launch times and AD overhead is on the order of nanoseconds, if anything, and that's only the method dispatches that we're dealing with at that point. Now, limited support and uses of Julia for research. Absolutely, I can see how that is a fair concern. But as I showed you earlier, that stance is not really how the progress has been. So as I said before, there are I would actually recommend you go check out. So on juliacomputing.com, you can go over to the case studies tab on there, and what you would find is there's a bunch of case studies from a bunch of different sources, which basically show the adoption of Julia in a large array of applications. So is it really a time to switch to it from these frameworks? Absolutely, yeah. Yeah. And I know my view can be biased, but the thing is, it really depends also on the kinds of workflows that you're dealing with, right? So like uh, if your interest lies largely in doing something like transfer learning, where you have a predefined model already, where you have a trained model, and that's all that you're interested in doing is fine tuning it on certain new data, then sure, you can do it in any of these other frameworks and it will net you no benefit. But the minute that you want to do anything beyond that is when you start, fighting with these frameworks so that, you get your way rather than being limited by them. And that is where I feel the generic and the easy approach that Flux and Zygote provide, which is what sets it apart. Yeah.
Okay, so we have one question from Satish Upadhyay in Q&A. Can you please tell me on how to be a data scientist at certain company? If I'm currently pursuing a BTech, maybe a simple pathway, or what can the undergraduate bachelor people start in learning? Maybe start with Julia or Python, or go on with courses.
So a lot of it, has to do with what kinds of areas that you are targeting, right? So like there is not just one kind of data science out there. There's many different things that many different companies do, and depending on what you want to do, you have to make sure that you have the expertise required. So be that in a language that is popular at the company today, or something that they would benefit from potentially. So like we know of many cases where we deal with companies all the time that have little to no exposure to Julia, but they are looking for the benefits. And what they do is they start with a small project essentially to see the kinds of learnings that they can get. And if the market is to be believed, it seems like for many cases, obviously you would have things like you know Python, which have the ecosystem, which have the support already, will continue to be what people want to go and what people will gravitate towards. But the thing is, the second that they start hitting the limitations, which is happening more and more today because of how competitive the landscape has gotten, you would need to transition to some kind of software which is going to net you those benefits, and that's where Julia becomes a very important factor in pursuing anything, not just data science. And I say anything because, anything in the sense, anything that you know the the problem set demands. So for things like systems programming, maybe it's not Julia at that point. Maybe it is something else. Maybe for if you're doing web development specifically, then maybe not Julia. Maybe you want to go for something else. But that is not to say that Julia does not have those capabilities or that mature ecosystem. It only serves to say that there are you want to suit the tool to the job at hand essentially.
Okay,
So yeah.
so one important question I just see here: why don't Julia community push Kaggle team to get Julia there? We see a lot of
Oh,
competitions, so why not Julia there?
so as a matter of fact, Julia was supported till sometime some years back, but the fact is really that Kaggle's business demands have become something that sells GCP more than their cloud is what they're more focused on. And of course, there's a lot of interest even to this date. There is a thread on the Kaggle website on their feedback section, which has we want support for Julia, and you have hundreds of people who have expressed that interest. And when they see the need, they'll do it. But I don't think that's something necessarily that will hold back its adoption.
Okay, so just a small question. That why? What are the pros and cons of taking learning Julia and not Python? Will Julia take over Python in some time?
Uh, so the fun thing about that question is that there is no right or wrong answer there. Okay. Will Julia overtake Python? What does overtake mean? Why would it do that? Is there reason for it to? And even though it may have all the technical merits that it wants, at the end of the day, what really matters is, again, you have to suit the tool for the job, right? And if you know users see the need for the performance from easy code, from the dynamic code, yes, at some point in time, you will see that adoption uh, increase by a vast margin. Already we see exponential growth. So there is reason to believe that Julia in any way is going to go away, so to speak. But at the same time, you know, will it overtake Python is a question which I might be too biased to say yes, but from the technical merits and the kinds of work that we see people doing, there is every reason to believe that as long as people keep developing state of the art software, then more and more people will gravitate towards it, right? That's just the nature of things. And not just that, so we have very excellent inter uh, interlanguage compatibility. So what that basically means is that you can call Julia from Python and Python from Julia. So it is very likely that the first kinds of adoption that you will see from people who work with Python is that they will write a very small part of what they would have written originally in C, or like the engineering team would have written in C, but they would have written Julia. And at that point in time, you'll have like a Python API over on top of Julia, and then slowly and steadily they'll see that okay, the APIs are basically mirrored. So like I don't really need to call Python at that point at all, right? So I might as well run this whole thing in Julia, then I see another part, and then I see another part, and then it's Julia all the way across, and we see that many times of So that's an interesting way that this has happened.
Okay, so great. Thank you, Dhairya, for joining us. And we are on time. I would like to thank you for giving your time to come here and give this wonderful, inciting talk on Julia. And maybe I hope many of the participants today will surely try to use Julia in the coming time. Thank you very much for joining in.
Thank you. Happy to be here.